All right. Good morning, everybody. Welcome back to Abstract Algebra. Oh my gosh, I forgot to draw the lines. The lines separating us from madness. Plan for today is we're going to talk a little bit more about normal subgroups, and then finally get into what it means to take a group G and divide it by a subgroup H. It's going to give us quotient groups. As far as office hours go, I'll have my usual hours on Monday before class and at 2. As far as homework goes, homework 6. Oh, okay, that was a joke for earlier. Dr. Murphy were saying something about like homework due tonight, so I thought I'd write that down. But you don't have any homework over the weekend. Take the weekend off. Do something else. Relax or something. There'll be a new homework waiting for you on Monday about set, the card game set. Yeah. Any questions or comments before we get started today? Okay, so a statistician and his client sit down for the first time. So a consultant. See, client says to the statistician, "Hey, look, I desperately need your help doing blah blah stats blah 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 thing. What are your fees?" The statistician says, "Oh, my fees are $1,000, and if you give me $1,000, I'll answer 3 questions for you." And the client says, $1,000 for 3 questions? Doesn't that seem a bit steep to you? The statistician replies, "Oh, I don't think that's steep. Now, what's your 3rd question?" Moral of the story is statisticians are like genies. You should be very careful what you say to them and ask for. Okay, so last time, in the second half of class, we started talking about normal subgroups, where we said that H is a normal subgroup of G, i.e. H, and our symbol for that was a little triangle with a line beneath it, G, if all of the left and all of the right cosets of H are equal. Meaning if you take any element, little g and g, little g times H as a left coset gives you the exact same set of elements as H times G as a right coset. And last time we looked at a couple examples, an example of something that did form a normal subgroup and something that did not. And today, I'm going to start off by proving this theorem on the second page of the packet, which says, if H is a subgroup of G, then H is a normal subgroup of G, if and only if little g, big H, little g inverse is a subset of H for all elements little g in our group. Or you may recall this set right here is just defined to be the set of all elements of the form little g, little h, little g inverse, where H can be any element from big H. So in other words, if it's the case that when we take an element in H and multiply it on the left and by the right by an element G and the inverse of that element, and if we start with something in H, multiply on the left and right by G and G inverse, and still always end up back in H, then that's equivalent, logically speaking, to H being a normal subgroup. And if there's some element, little g, that breaks this, then big H is not a normal subgroup. And this is something, you may recall this set showed up on homework 2, the last question. I asked you to prove things like this forms a subgroup, if and only if H is a subgroup, etc., etc. Today, that's going to come back and it's going to give us a useful way to kind of tell if given a subgroup H, when is H going to be a normal subgroup of G, rather than having to check each individual coset. So let's prove this. Elaine, you've been bothering me. Which direction do you want to prove first? We've got an if and only if statement. You want to go left to right or right to left?
Left to right.
Left to right, all right. So we're going to start by assuming H is a normal subgroup of G, and then from there we're going to prove that if we take any product of things of this form, we are always going to get something back in H. So we're gonna let H be a normal subgroup of G, and I'm gonna take a little g as an arbitrary element in the group G, and our goal is gonna be to show this thing, that it, little g, big H, little g inverse, has to be a subset of H. Well, so to do that, we're going to let little g, little h, little g inverse be in that set, G inverse, which, if this element, gh, g inverse, is in g, big H, g inverse, what has to be true about little h? According to the definition of how this set is defined, what would H have to be an element of in order for GH G inverse to be in G big H G inverse? Yep. Because basically what we need to do is we need to show that this thing is an element in H. If we can do that, then we've proven the left to right direction. So what do we do? We know since H is a normal subgroup of G, we're going left to right, so we can assume we have a normal subgroup. Little g times big H is equal to big H times little g. That's just by definition of normal subgroup. So since little g, little h is contained in this left coset, little g times big H, that's just by definition, since H is in H, little g, little h has to be in little g times big H. And since that left coset, little g times big H is equal to big H times little g, since little g times little h is contained in this coset right here, big H times little g, that means there's a particular way that we should be able to write this element out. How can we write this element out as in the form something that would be in this coset? Okay.
HG.
Little h, little g? Yeah, things in here would look like little h, little g. So little g, little g, little h has to be equal to little h, little g. Except that's wrong. Doesn't necessarily have to give us back the same little h, little g. Just because gh, little g, little h is in this set, doesn't mean it has to be equal to the same little h times little g. It just has to be equal to some element in h, some element in the subgroup big H times little g. Not necessarily the same little h, just because it's in here. If big H has more than one element to it, it could be equal to anything else at H times that g. It could be the case that H prime and H are equal. That's certainly possible, but it's not guaranteed to be so. Does that make sense? I'm on board with why we need a new element here in big H. All right, so we know that. So we know little g, little h is equal to h prime g. But then we could take little g, little h, g inverse, and that'll be equal to this thing times g inverse. H prime g, excuse me. I'm making the same mistake I said not to make. And what's little h prime times little g times g inverse going to give us? Or to multiply that and simplify, right? Yeah, the g and the g inverse, with the old swoosh swoosh, is going to just give us h prime, which is an element in the subgroup H. And then we can say, thus, little g, big H, little g inverse is in fact going to be a subset of H for all elements g inverse. The reason being, because we took an arbitrary element in this thing, And we took an arbitrary element in this set and showed that an arbitrary element here has to be an element in H as well by itself. And since we did that, and that tells us this thing is a subset of that thing, since everything in the first set is contained in the second set. And that's our left to right direction. Any questions, comments, concerns? All right, do the other one. Otherwise, pretty similar. We now get to suppose that little g, big H, little g inverse is always a subset of H for all little g in our group, and our goal is going to be to show that H has to be a normal subgroup of G. If we can do that, that would complete our if and only step. So now what I'm going to do is I'm going to make a new element A. Just let A be an arbitrary element in our group G. Then I claim, given any H in H, what can we say about A inverse? Using our starting assumption. If little h is an element in big H, and A is any element in our group, what can we say about this element here? In particular, what set does that thing have to lie in? In H? Has to lie in H, because this thing is going to be an element in a big H A inverse, which itself is a subset of H. Hence, little h, little A inverse has to itself be an element in H. Let's just say, I better write this. I'm going to say that's equal to H. Sound good? Because it has to be an element in H, we can just set it equal to little h. Wayne, you disagree?
No, I think that's fine.
You think that's fine?
I would like it better if it was like H.
I think we have to make it H prime.
Oh, thanks.
Because just because this thing is contained in H doesn't mean it has to be equal to the same little h that we started with. Don't fall for the same trap more than once. Already tricked you once. Shame on you, shame on me, something.
You've tricked me hundreds of times.
Oh, yeah. So specifically, little h, little A inverse has to be equal to some elements in H. They could be equal to the same original H, if say A and H commuted with each other, but since we don't necessarily know that they do, all that we can say is A inverse has to be equal to H prime for some element H prime in H. So what does that mean? Since little h, little A inverse is equal to H prime, what can we say about this little a times little h? How can we rewrite this equation to just say something about little a times little h without the A inverse text on the left-hand side? Right?
Little h prime A.
Yeah, and little h is going to be equal to little h prime A. I just realized something I don't like. I'm going to make a slight change to the second line and say, given any element in this left coset, little a times big H, little a, blah, blah, blah. Doesn't really change any of our arguments so far, but it's going to make it nicer to make a point here in a second. So we know that A equals ha, hence little a, little h has to be an element of the right coset of H multiplied by A. Because little a, little h is equal to something in H times little a. But what have we shown? We've shown, given an arbitrary element in this left coset, little a times big H, we've shown that arbitrary element there has to also lie in this right coset, big H times little a. And so, since that's the case, we could say this left coset has to be a subset of the right coset. Little a times big H has to be contained in big H times little a, because we just showed that every element in this first thing has to also be an element in the second thing. Any questions or comments so far? So we've shown that everything in the left coset has to be in the right coset here. You could basically do a very similar argument to show everything in the right coset is also in the left coset, that I don't feel like writing out. Okay, similar argument. Big HA is contained in A big H. Hence, these two cosets are equal. And if you remember, what we need for a normal subgroup, if H is a normal subgroup, then the left cosets of H all have to be equal to the corresponding right cosets of H, which we just showed is the case since A could represent any element. Since this is true, for all elements in G, H is a normal subgroup. And neato mosquito, we are done. Questions or comments? Or concerns? As long as there's no all-out panic. So this tells us we have an additional equivalent condition, a way of saying that H is a normal subgroup of G. If we take anything of this form and know that anything of this form always ends up back inside H, then that's another way to tell we have a normal subgroup. All right, y'all ready for the big one? Time to define quotient groups. The textbook calls these factor groups instead of quotient groups, but they mean the same thing, and I think factor group sounds stupid, so I'm going with quotient groups. But if you're following along in the book, and the book starts talking about factor groups, it's the same thing. It's just a different name. I like quotient better because it sounds like there's some dividing going on, whereas factor groups just sound like there's multiplication going on or something, which doesn't tickle my fancy as much. So now we're finally going to talk about how to take a group G, divide by a subgroup H, and get a new group. And basically, the idea is we're not actually doing division of anything. It's just a symbol as a division. But what we're really going to be doing is we're going to be making a group out of the cosets of H. And so here's how it goes. We're going to let G be a group. And we're going to let H be a normal subgroup of G. And this is why we talk about normal subgroups, because what we're about to do only works with normal subgroups. And we'll discuss why that is in a second. Then, the set, which you're going to read as being G mod H, which I'm just going to define to be the set of all left cosets of H. If we take the set of all the left cosets of H, which, since H is a normal subgroup, is going to be the same as the set of all the right cosets, under the operation, we're going to define a binary operation here, where I'm just going to take little a times H multiplied by little b times H. I'm going to set to just be equal to little ab times H, is actually going to form a group called the quotient group of G by H. In other words, if we take the set, given a normal subgroup H, if we take the set of all cosets of that subgroup, that set of all cosets is itself going to form a group. Is that? Any questions? Look like you had a thought.
I just started writing this down and then I was like, I thought you write it down.
Ah, so it is. How generous of Dr. Burstel to write some stuff down for us. So let's look at an example. So let's consider the case where G is the dihedral group G4, H is just going to be the subgroup that contains the identity element and R squared. And I want to look at what does the group structure look like if we take G and mod out by H. Is that what we did on the front page? I don't remember. No, it isn't. I'm just going to tell you that H is a normal subgroup of G. If you don't believe me, that's fine. So let's look at the elements. What do the elements look like in G mod H? Well, we said that the elements in the quotient group are just going to be the left cosets. And so, how many elements are going to be in G mod H? Meaning, how many left cosets does our subgroup of order 2 have in our group of order 8? What does Lagrange's theorem tell us? Okay.
16?
It's not division.
No, 4.
It's going to be 4. Because by definition, the number of elements in G mod H is just going to be the number of left cosets that H has in G. Just because that's, well, G mod H is made up of the left cosets, so the number of left cosets is the number of elements in our group. Which, according to Lagrange's theorem, is just going to be order of G divided by order of H, which is 8 over 2, which is 4. By the way, does this make you feel warm and fuzzy? It makes me feel warm and fuzzy because the reason why we use this notation G/H to refer to this group is mainly because it satisfies this equation, that the number of left cosets, according to Lagrange's theorem, is just going to be the order of G divided by the order of H. And this were fractions. If G and H were like integers instead of groups, that would be the equation that holds. So like the absolute value of A over B is the absolute value of A divided by the absolute value of B. When we replace A and B with groups, it takes on a very different meaning. It says the number of left cosets of H and G is equal to the number of elements in G divided by the number of elements in H, but the same basic equation still holds. And that's why we use this notation to refer to the group of left cosets. It's because it makes that equation warm and fuzzy. Let's write them out. What's left coset of H in D4? Hey.
EH.
H itself. So if we take EH, well, that's just E times E times R squared, which is E and R squared. Yay! What's another way we could have written the same coset?
HE.
F equals E. Yep. Give me another way to write it as a left coset.
R squared H.
Yeah. You could also say that this is going to be equal to R squared H by the same reasoning. If you multiplied E on the left by R squared, you get R squared. If you multiplied R squared on the left by R squared, you get R to the fourth, which in D4 is equal to the identity. So there's one element. Somebody give me another be another left coset that we could go with? Yes, Elaine.
RH.
RH is another one. So that would give us R times E and R times R squared, which is going to be equal to R comma R cubed. What other left coset is this going to be equal to? Indeed. Here we're using the property way back from the cosets packet that says that any element well, let me put it this way. XH is equal to AH if and only if X itself is an element in AH. We had that as kind of one of our properties back in the coset packet. So since R cubed is an element in RH, that means R cubed H and RH have to be the same thing. So I'll go ahead and give you the other ones. I also have SH that we can go with, which will be S times E and S times R squared, which is the same as S and R squared S, which will be equal to R squared S times H. And the last coset, by process of elimination, is just going to be little rs times H, which will be little rs times E, little rs times R squared, which is going to give us little rs, rs R squared is equal to SR cubed R squared, which is going to be equal to SR, which is equal to R cubed S. And so we will get the same coset here as R cubed S times H. And boom, there's all four of our group elements. H itself, which is just equal to the identity times H, little r times big H, little s times big H, and little rs times big H. We could take other elements in D4 and take the corresponding left cosets by multiplying H on the left by, say, R squared S, but that would just be giving us the same thing as S, little s times big H, so we don't need to include it more than once. And our group that we're going to get gonna say, as a set, this is just going to be equal to H, RH, SH, and little rs times H. And yeah, that's our group. Let's see what happens if we take a couple little group operations here. Which element in this group would we get if we took the left coset RH and multiplied by the left coset SH? According to our group operation, which I just erased. Here? Yeah, we're just going to get the same thing as if we taken little rs times H, by definition. To multiply two cosets, just multiply their corresponding elements together. What would we get? Here's a little more fun one. What would we get if we took SH and multiplied by a little rs times H? Well, we would multiply the elements and get little s, little r, little s times H. Is that one of the elements in our group? Better be. We have a, unless, better be. I claim this as a group, so it better have closure. So let's see. SRS is going to be equal to R cubed S times S H, which is just going to be R cubed H. Uh-oh. Is r cubed h equal to one of these things? Which one?
Orange.
Okay, good. We did get something back in there. I did not violate code. So here's our group. One of these cosets is going to give us our identity element. It's a group. I said it's a group, so it better be able to find an identity element in here. Which one of our 4 cosets do you think will give us the identity element? Meaning, if you multiply the left coset by anything else, and by any other coset, you just get back that other coset. Alright. And the identity is just going to be h, which if you want, you can write it as e times the identity element in G times the coset h. The reason being, since for any element little a times big H in or for any little a times big H, an element of our group, so for any left coset of H, if we were to take H times little AH, that's the same thing as taking little EH times little AH, which will just give us little EA times H, which is just going to be AH again. And then similarly, little AH times H will also just give us back little a times H. So the identity element in the quotient group, G mod H, is always just going to be H itself. Or if you prefer, H multiplied on the left by the identity element from your original group. So this is going to be something, this is going to be something that'll work as the identity element in any quotient group. Just take H itself. How about inverses? What would the inverse of an arbitrary element little a h inverse be? Every time I say little a, I want to say little a.
You should.
Don't be ridiculous. So what coset, and this is something that's true in general, what coset of h would I need to multiply little a times big H by in general that'll get us back to just plain old big H? Okay?
A inverse H.
I think so. Because if we took little AH times little a inverse H, we're just going to get little a times little a inverse H, which is just the identity times H, and that gives us back H, which is the identity element in our quotient group. So finding inverses is pretty straightforward. To find an inverse of a coset, you just need to take the inverse of that corresponding element. All right, so we did that here. So if we did that here, in this case, what we would get is we would get that H inverse is equal to, well, just H, because H is the identity element, so its inverse is itself. What would the inverse of little r times big H be? RH. Same thing? Well, we should get r inverse times H. R inverse in D4 is going to be r cubed H. Oh, hey. We said that r cubed H and RH produce the same coset. So yeah, I would agree. Similarly, this is actually an interesting group in that every element is its own inverse. Inverse equals and inverse equals first. mainly because if you take the inverse of s, you're going to get s itself again. And if you take the inverse of little r times little s, you're also going to get little r. You're going to get r cubed s, but little r cubed, but r cubed s times h is the same as rs times h. So every element in this group is known as. So this group is actually something we've seen before in a different context. If you want, you can check for yourself. But this group's actually abelian. In this case, in general, quotient groups do not have to be abelian groups. It just so happens that that in this case, G mod H is abelian. The reason why is because I specifically chose H to be the center of the group G. The center of the dihedral group D4 consists of the identity element in R squared. Okay. And G mod H has 4 elements in it. So what group is G mod H can be isomorphic to? We have a nice theorem that tells us something about if you have an abelian group of order 4, it has to be isomorphic to one of these things. Because by our good old friend GAG, fundamental theorem of finite abelian groups, we have 2 possibilities for what G mod H could be isomorphic to. What are our 2 ways of taking Z mod NZs and taking direct products in a way that'll get us an abelian group of order 4? Right?
Z mod 4Z or Z mod 2Z, direct product Z mod 2Z.
Like that? I agree. Yeah, there's only 2 abelian groups of order 4 up to isomorphism, meaning one of these 2 things. And I claim G mod H is isomorphic to one of these 2 things. I want you all to do, take a minute, see if you can find out which one of these things you think G mod H is isomorphic to, using some of the properties of G mod H that we've already shown. Here's a hint, don't try and find a direct isomorphism. Or don't try and find an explicit map phi that's an isomorphism. That would make you sad. Instead, see if you can use some properties of G mod H from what we've already looked at for this specific example, and then see which of these 2 groups will have those same properties. So go ahead and take a minute and think about it, and we'll come back together in just a second to talk about it.
The other one.
I just want to find.
Right, I mean, because like you got 0, 1,
Yeah.
0, 1, then you got 0, 0. Same with 1, 0, 1, 1, 0.
So, does anybody think they have an answer to which of these 2 groups is G mod H can be isomorphic to? Okay,
Second one.
explain.
Because each thing is its own inverse.
And this one, but not in that one?
Right.
Yeah. Since each element is its own inverse, G mod H can't have any generators. Because if you multiply something by itself even once, you're just going to get to the identity. And so, turns out G mod H is going to be isomorphic to Z mod 2, direct product Z mod 2. Since out of these two possibilities, Z mod 4 is cyclic, but G mod H is not cyclic. Since every element is its own inverse. So this is kind of nice. We were able to use the GAG, the fundamental theorem of finite abelian groups, to kind of process of elimination our way to saying that G mod H, our abelian group, has to be isomorphic to this direct product, Z mod 2 plus Z mod 2. Thank goodness G mod H is abelian. Made it classifying it a lot easier. Do you know how many non-abelian groups of order 4 there are of isomorphism? Imagine how many? Hey, you want to guess?
It's 0.
Yeah, it's 0. Turns out every group of abelian 4 is abelian, so that's another reason why I knew this group was going to be abelian, is because it had order 4, therefore group order 4 abelian. We haven't proved that yet, why there are no non-abelian groups of order 4, but it's going to turn out to be the case that anytime you have a group whose order is a prime number squared, it's going to be abelian.
What?
Heavily related, by the way, to the number 3 part B on the homework that was due on Wednesday. Something to discuss later. Any questions or comments on this group? Sorry, I should have given you more room in your packet for this problem. I ended up doing a lot more than I kind of intended to do. I went with it. All right. Nick, I can hear your thoughts. You are wondering right now, why did we require that H was a normal subgroup of G? That was what you were thinking, right?
Yes, definitely.
Good. So now, we're going to prove, I can't let you go now, it's too much time left. We're going to start proving that G mod H will always form a subgroup, and our proof is going to rely on the fact that H has to be a normal subgroup of G in order for this thing to actually give us a group. So let's prove, in general, if H is a normal subgroup of D, then G mod H is a group. And our proof is going to rely on H being a normal subgroup. So what do we need to show? I think we could say that closure and associativity are going to be pretty, we don't really need to prove anything, because closure and associativity just kind of follow from the fact that G has closure and associativity. So closure and associativity follow from G having these things. Because if we take some AH times some BH, then the fact that little a times BH, the fact that this thing is in G mod H, this comes from the fact that if A and B are elements in G, then A times B is an element in G. And similarly, I really want to write this out. AH times BH times CH is going to be equal to AH times BH, and then that expression times CH is going to always be true since AB times C is equal to A times BC for all A, B, C in our group. So subjectivity is actually pretty easy. It just follows pretty quickly from the fact that our group G, we're assuming, has associativity. We know what the identity is, and we know how inverses work. We talked about that earlier. The ID we already showed on the last page is always just going to be H, or EH if you prefer. For inverses, we know every element has an inverse. AH inverse, we said, is just A inverse times H. And so boom, we have closure, we have associativity, we have identity, and we have inverses. So that's enough to give us a group, right? Why are you assuming no?
Because of your tone.
Because what?
Because of your tone. To be trying to trick us again.
All right, fine. Which group property am I missing? You don't got any. You have no answer to that, huh, Lauren?
I don't have an answer for a lot of things.
So Nick is once again thinking the exact same question. Dr. Gerstle, why did we need a normal subgroup? Because nowhere in these four things did I use normal subgroups. There is something else that we don't have yet, and it's something insidious that we don't usually have to check in a group. Anyway.
We have to check if it's non-empty or not.
Well, it's not empty from the fact that H, okay, that's also true. This group is not empty because H is always an element in it. I didn't even think about that one, but it's not empty. We have to check that our group operation is well defined. It's not obvious at all that it is. And that is going to be where we need a normal subgroup is going to come into play. And that we'll do on Monday. Have a good day, everybody, or have a good weekend, everybody. I'll see you all on Monday.